time is it? Okay, let's get started. Everybody okay?
Yeah.
Happy? Okay, so I have way too many slides for today's class, so I probably won't get through them all, so I'm going to talk fast. And I talked to several of you after class last time who complained that I was talking too fast. So if something goes by and you have no idea what I just said, just raise your hand and say, what? Okay? And just make me say it again, all right? And make me slow down. Okay? Good? All right. So last time we talked about irregular expressions and finite state automata. What I'm going to try to get through today is a few more technical details and algorithms about how to manipulate finite state automata, and then finish up with some motivation as to why anybody would care about this stuff with respect to human languages. And the latter part will be a little bit in Chapter 3. So in terms of readings, what you should be keeping up with is Chapter 1, Chapter 2 in the book, the beginning of Chapter 3 in the book, and the new version of Chapter 2 from the draft for the new edition. Okay? All right, so going back to where we were last time, we talked about non-deterministic machines and the fact that there's basically two ways that we can go about trying to do recognition with non-deterministic machines. And what I mean by recognition is regular languages define sets of strings. We want to be able to separate out the sets of strings that are in the language from the sets of strings that are not in the language. So when I say recognition, what I mean is we've made the judgment that this string is in and this string's not in. All right? So there's two ways of going about doing that. We can either take the non-deterministic machine and turn it into a deterministic machine and do what we did before, or we can modify our deterministic recognition algorithm to handle non-deterministic machines. We'll cover that first. Okay, so just to refresh your memories, this is the simplest version of a non-deterministic machine you're ever going to see. But if you're in state Q0, you're looking at the tape, you see an A, you don't know what to do. Right, so there's lots of different practical purposes where this shows up, and this is just a very simple illustration of it. So for non-deterministic recognition, I'm talking about this notion of a path through the machine. The way to think about that is you're just moving your finger through the machine, and you're looking at the tape, and you're saying, well, I'm in Q0, I'm looking at a B, so I can go here. That's what I mean by a path through the machine. With a non-deterministic machine, for a tape that is to be accepted, a tape that is in the language, that means that there is some path through that gets you to the end of the tape and ends up in a accept state. In order for us to reject the string, we've got to try them all. And when I'm talking about a path through the machine, I'm saying a path through the machine that is being driven through the machine by the contents of that particular input tape. So if I get a B and a B, then I stop immediately because there's no path going forward. If I get a B and an infinite number of A's, then I'm in trouble because I have an infinite number of A's. But if it's a large number of A's, sooner or later I'll get to the right place, as long as there's an exclamation point at the very end. Good? All right. So I'm not going to say all the words on this slide, but you should memorize them. Right. So success means finding a path. Failure means not finding any path. Good. So back to our example. We have B, A, bang, and I'm going to use the backslash to mean that's the end of the tape. What we want to do is we want to be in state 4 looking at that end of tape marker. So the right way to do this is to Q0, Q1, Q2, Q2, Q3, Q4. The ambiguity comes when I'm in Q2 looking at that A, I don't know what the right thing to do is. Right? So we went through this last time. I'll just go through it really quickly. This illustrates making the wrong choice here. So I'm in Q2. I'm looking at that second A. Remember, the first A gets us to Q2. So there's no ambiguity when we see the first A. So when we see the second A and I'm in Q2, now I don't know what to do. And in this particular example, I'm first going to make the wrong choice. I'm going to go to 3. And I know that if I go to 3, I'm doomed because there was another A to be consumed. So I'm not prepared to look at the exclamation point because it's not there. The A is there. Right? So that's a failure. The way we know this is a failure is because now I'm in state Q3, and if you remember, if you look at the machine, does Q3 know what to make of an A? No, there's nothing in the transition table that says, if I'm in Q3 and I'm looking at an A, I should go here. The table simply says, if I'm in Q3 and I look at an A, the cell is empty. That means I need to reject. Does it mean I need to reject?
No, we need to
We need to see if there's any other paths, right? We can't, because it's non-deterministic, the fact that the cell in the transition table is empty doesn't mean reject immediately. It simply means there's no place to go from this path. But if there are other paths that are yet unexplored, we should explore them. Good? All right, so let's finish that out. This is the way ND recognize is going to look. It's in the book. Now, the main reason I'm going to spend a certain amount of time going through this is because this is, you should think of this as sort of being a prototype. It has all the elements of what we're going to need going forward every other time during the semester when what we need is some kind of heuristic search. Because in effect, this is going to turn out to be a heuristic search. And I'll point out some of the places where things are kind of vague in this. So let's see if I can get the pen to work. Everybody see that? All right, so it takes a tape and a machine as input. Now remember, just as last time when we talked about the feeding a transition table into the machine, this is a universal algorithm, just like what's underlying grep in Unix. It gets specialized because you're giving it a string to be recognized, and you're giving it a machine that's going to do the recognition. The algorithm itself is constant. It doesn't change.
So the machine, in this case, is it a set of states or is it a transition table that you're in?
I'm going to try to keep one of the things that will annoy you as you go forward, especially when you start doing the homeworks, is that the algorithms in the book are extremely vague. They're pseudocode, which pseudocode usually means the parts that are too hard to describe, we just sort of lapse into English and you have to figure it out. So in this case, you should assume that when I say machine, I'm passing in a transition table. So you know the alphabet, you know the number of states. Somehow or another, the accept states are marked. The final states are marked. It's all sort of there somehow. But in the simplest terms, this is just a transition table. And the tape is just a string, right? We can just march through the string. So the first thing we're going to do is create a variable called agenda, and that is your first clue that this is going to be some kind of a search. And it's kind of a funny notation here, but basically what I'm saying is let's create a state. That state consists of two things, and here I'm overloading the word state, so I apologize. There's going to be states in the machine, and there's going to be states in the search. So what we're creating here is a state in the search, and it's going to consist of two things. Where am I looking at the tape, and what state of the machine am I in? Got it? So for us, this is going to say, and for whatever reason, the example, we start with 1 with the strings, we start with 0 with the machine. So again, I apologize for that. So this is going to consist of Q0, 1, meaning the state that I'm looking at, the state that I'm residing in the machine is the state Q0, and the place I'm looking at the tape is the beginning of the tape.
But non-determinism can have multiple start states also.
Yeah, let's not worry about multiple start states for right now, yes. We can have multiple start states. The way we'll get away from multiple start states is if we have multiple start states, we create a new start state that's a single start state with epsilon transitions to the multiple start states, which adds even more non-determinism, but makes the problem go away.
How do you define the location where we are in the tape? Like the second parameter in agenda is the location that we are currently looking at in the tape.
Right.
So what is that? Is it the character we are looking at, or is
it's the character we're looking at? Yeah. And we'll just imagine it's a pointer. So
okay.
The tapes start at 1 and they go to however long the tape is. Okay? So we have Q01 to get things going. Then we're going to assign a variable called current search state, which is just going to call something called next, which takes something off the agenda, the next thing on the agenda, and assigns it to current start state. All right, how does next work? I'm going to be ambivalent at this point. Minimally, you should think of it as doing a pop, because there's only one thing on the agenda, at this point because I only put one thing on, and now I'm taking it off and assigning it to current search state. So it's going to do a pop. And so for this part of the example, it doesn't really matter how I choose which one I'm going to take off because there's only one thing there, right? So think of it as pop. So once I do that, the agenda is now empty. I put one thing on, and I took one thing off, which seems like a silly thing to do, but bear with me. Good? Okay, then we're going to go into a loop, and we're going to say, well, that thing that you just took off the agenda, is it an accept state? If it is, then I'm just going to say, cool, accept, right? Because we're going to accept in non-determinism, we're going to accept as soon as I find the first thing that puts me in an accept state, where accept is going to be at the end of the tape, and is the state that I'm looking at an accept state.
I was just going to check the end of the tape thing.
Yeah, so we're at the end. We have to know when we're at the end of the tape. So there's that silly marker or something. We can tell when we're at the end of the tape, and among all the states that are in the machine, the ones that are final accept states are marked as being final. So implementing an accept state is going to be pretty easy, but it's left undefined here. All right. Clearly, in our example, B, A star, we're looking at a B. We're at the beginning of the tape. We're not in an accept state. Okay. All right. So if that's not the case, then what we're going to do is we're going to update the agenda by calling generate new states. How is generate new states going to work? It's just going to consult the transition table. Transitions table says, I'm in Q0, I'm looking at a B. What do? I go to Q1, right? So the new states are going to consist of, now I'm not in Q0 looking at tape position 1. I'm going to be in state Q1 looking at tape position.
Next one.
Either or the next state.
No. So the states in the search space consists of a tuple, two things. One is the state in the machine I'm in, and the other one is a point on the tape. So if originally I was in Q0 looking at tape position 1, which is a B, what's the next state going to look like?
Q0 and 2.
2, right. So it's going to be, we're going to go to state Q1, and we're going to look at tape position 2. So whenever I look at something and make a transition, I'm going to update the pointer on the tape to look at the next position on the tape. So we're going to march through the tape. Unless it's the other kind of non-determinism, where that epsilon means I'm allowed to transition to a new state without updating the tape. But that doesn't come into play in this example. So we're going to go to tape position 1, tape position 2, tape position 3. We're going to march systematically through the tape, keeping track of where we are in the machine and where we are in the tape. Now, if you remember this guy, at the beginning, we're in Q0 looking at B. There's only one place to go. It's Q1. So generate new states is only going to generate how many states? One. Right. So at the beginning of this, there's a kind of peculiar behavior that you'll see. And often searches that are heuristic searches have this characteristic where sometimes what we're doing is there's one thing on the agenda. It's not a goal. We're going to generate new things to look at. Often we only generate one new thing to look at. We put it on the agenda, then we pop it off the agenda. So the agenda has this behavior of just staying narrow, right? But once we get to interesting problems, what's going to happen is, and again, this should be familiar to you from your algorithms classes, we're going to pop one thing off the agenda, then we're going to generate 10 things and put them all on, and then we're going to loop, pull one thing off, and generate 100 things, put them on the agenda, and then pull one thing off and generate 1,000 things. That's when we run into trouble, and that's what we'll get to at the end of the semester as we go through the semester. Good? Right. So we pull one thing off. We check to see if the agenda is empty. How might the agenda be empty at this point?
There are no transitions.
No transition.
Yeah. Right. Imagine I was at the beginning of the tape, and I was in Q0. I was looking at the tape, and the tape contained an A. So I would create my initial state. I would push it onto the agenda. I would pull it off the agenda by making it current state. I would ask, is current state an accept state? It says no. And then I ask generate new states to generate me some new states. I look in the transition table, there's nothing there, so nothing gets added. Now the agenda is empty. If the agenda is empty at any point when I reach this, it means that I got no place to go. I have reached that point where I can determine that there are no ways forward. If there's no way forward, then it's a reject.
So in the previous step, we are calling generate new states. So that will return us a set of states, and we are computing the union with the present agenda.
Right.
Is there a situation in which the present agenda is empty?
Well, yeah, right. So we can union it
If
with.
not empty, the union will never be empty.
We can union the empty agenda with new stuff and get it just consists of the new stuff. You think of the union as being just add some more stuff on.
Yeah.
So if it's empty, if we generate 3 new states and it's currently empty, we wind up with 3 new states. Everybody happy? Sort of? Okay. Now, there's a couple of places here where if you were to implement this, you would want to know more details. I'm leaving next completely undefined, and this union should be a little bit worrying. So again, going back to your algorithms classes, there's a couple of ways I can resolve these ambiguities, resolve this ambivalence I have. I can make next just be pop, which means take the thing off the front of the agenda and don't worry about the order of stuff. And I can make that union be take the new things, put them on the front, take the new things, put them on the back. Or if I have some kind of heuristic, take the new things and stick them into the agenda in such a way that the agenda is being kept ordered according to some likelihood of having the most good stuff at the beginning and the most not good stuff at the end. I know that's very technical. Any questions? All right, so the basic loop here is start with some start state, see if you're done. If you're not done, generate some new states, put them onto the agenda, take the front thing off the agenda, see if you're done. If you're not done, take the next, generate new states, put them onto the agenda, take the next thing off the agenda. If the agenda is ever empty, then you're done. As soon as we find a single path that's an accept, we're happy. All right, so let's do an example. I know this seems a little tedious. How many people think it's tedious? Okay, you can supper. All right, so this example, right? So that's our initial state. We're in Q0 looking at tape position 1. This is the current state variable. Initially, it doesn't have anything in it. We've created this. We assign that to that. So now the current variable is Q01. The agenda is empty because there was one thing on it. I popped it off, so now it's empty. Generate new states creates Q1 looking at 2. Yeah, that actually reminds me of something I was supposed to announce. So on the tables in front of you, there are these little microphones. On the tables in front of you, there are lots of electronic devices, but there are these little mics. That is recording for the students who are elsewhere. So if you ask a question, that's how it's picking up your voice. But if you sit there banging on the table with your pen like this, what they're hearing is boom, boom. So don't do that. Don't spill coffee on it or anything else, right? So we're in Q0 looking at a 1. We're going to create a state, go to Q1 looking at tape position 2. That then gets assigned to current state, which leaves the agenda empty. That takes us to looking at Q2, looking at 3. That gets this. Now the agenda is empty. Now we're in Q2, looking at tape position 3, which is an A, which means we can either come here or we can loop back. So that's why the agenda is generate new states is going to give us 2 things. The 2 things that it's going to give us, we put onto the agenda some random order. In this example, the random order I put it in is the one that causes us to go awry. So we're going to say Q34 is the first one and Q24 is the second one. We already know Q34 is the wrong thing to do, but we're going to pop it off the agenda and give it a try. We know that that results in nothing good. Now, so what we're implementing here is a form of backtracking, but there's no explicit backtracking. The reason the algorithm works is because once we get to state Q3, looking at position 4, that's the one where I'm in the wrong state looking at an A. I call generate new states. Generate new state says I got nothing. Go back to the agenda. The agenda has this on it, which is where we should have gone in the first place. So it gets assigned here, and the rest simply plays out from there.
So what if we tested Q24 first?
Then we would have been lucky, and we would have gone through. If we had gone to Q24 first, meaning we had picked the right thing first, we would have found the path that leads to success. We never even would have looked at Q34, and we would have succeeded. So basically, on this path, you're saying, when I got here, instead of going down here, I'd gone down here, then I just would have gone a straight shot. There would have been no backtracking. There would have been no failure. And I wouldn't have to have even examined the other path. Now, the question is, how would you know that? Right? So what I was trying to say earlier was, in simple algorithms like this, we can afford, without the use of heuristics or without the use of probabilities, to simply put a static strategy on how I'm going to handle the agenda. And that's either basically going to come out to be breadth first or depth first. Put stuff on the front, put stuff on the back, and hope. If I put stuff on the back and I execute it with a breadth first strategy, probably going to run out of memory. If I put it on the front, I'm going to get nice stack-like behavior with minimum memory requirements, and everything works out well in the end. In realistic applications, and the canonical case that we'll talk about is in machine translation, where the tape is being driven by a sentence from the original language. What I'm looking for is a string of words in the target language, and I'm using a heuristic that says word 1 could get translated into the 50 different ways. I'm going to keep track of an agenda that has all 50 different ways of translating this word in English into this word in French. And then I'm going to go from there. So there, we're not going to allow ourselves to use depth first or breadth first, because neither one of them is going to work. We need something that says, when I generate these new states and put them onto the agenda, I need some idea that this option is better than that option. The ones that are better are the ones that are being put at the
Excuse me.
And I'm also going to need something that says, if I look at the entire agenda, once I get beyond option 120, things are looking so bad that there's no way they're ever going to get to the right path. I'm just going to put a limit on the size of the agenda, saying we're only going to keep the top 100. And if the right answer winds up falling off at some point to option number 101, then tough. I'm not going to worry about it. All right? And again, that's way in the future. So for right now, just make sure you understand how this works and go home and trace through each one of these states to make sure that everything makes sense. All right, so that's one way of doing it. Again, I said I'm going to talk fast, so is everybody okay with my torturing you? All right, so some people think I'm not talking fast enough. All right, so the other way of doing this, which is the way that's implemented nowadays in most grep-like regular expression library implementations, is based on something called the subset construction, which takes the non-deterministic machine and turns it into a deterministic machine. So we don't have to worry about the search stuff because we're back to derecognize. That simply says at every point in time, I know exactly where I'm going to go. All right? So the intuition behind the subset construction is the following, and it sort of sounds a little bit science fiction-y, a little bit quantum-like. You're a physicist, right? So when we're in Q2 looking at an A, we know we can either go to Q2 or we can go to Q3. So the way the algorithm is going to work is we're going to build a new machine where the way to think about it is we're going to consume that A, and we're going to go to both Q2 and Q3 in parallel. Now, if we could implement parallel machines, then that'd be fine. We just go both. And then if there's any future parallelism, we'll just follow those as well. And the first fringe in the tree that leads to an accept state wins. And if they all peter out and never reach an accept state, that's fine too, because they're all going to die out. So think about, I'm in Q2, I'm going to go to a new state, Q2, Q3. It's hard to put this into English, but that's the way it's going to work.
Similar to trying to manage memory during the search on your queue or whatever, it seems like this will also run into like a similar sort of memory constriction.
Yes. So there's the lazy way of doing this, and there's the right way of doing it. Nobody ever implements the right way. In the example I'm going to give, it's going to look like the lazy way seems like the right thing to do, but we'll talk a little bit about the complications for it. So yes, there's always time and memory. Those are death and taxes, right? I mean, you can't get away from them. I know you're all young. You don't think about taxes or death because you're not making any money and you're young. Right? So the trick is to think about simulating going to both at the same time. And the way to think about it is our original machine has 5 states in it, Q0 through Q4. So imagine in your mind a new machine that has all possible subsets of those states. So we start out with 5 states. We're going to generate a new machine that has the power set of all 5 of those original states. So we have Q0, Q1, Q2, Q3, Q4, Q0, Q1, Q1, Q2, Q2 through Q3, Q3, da-da-da-da-da-da-da, all the way up to Q0, 1, 2, 3, 4, 5. So it's the power set. The states in the new machine consist of the power set of all the states from the original machine. So 2 to the 5th states. Good? All right, so remember what we have to have in order to have a machine. We have to have a set of states, we have to have the alphabet, and we need the transition table. And we need to know which states are final states. But the transition table is the key thing. So if we're going to create a new machine that's got 2 to the 5th states, then I have to fill in the transition table for that as well. So we're going to talk about exactly how that's going to work. Everybody understand the power set business? Right? It's going to take all the states that we could possibly get by combining the original states in the original machine. So it's much bigger, potentially. Right? So we're going to have the original non-deterministic machine has the usual parts, the states, the alphabet, the transition function, start state, and accept states. We're going to construct a new deterministic one that accepts the same language. The states in the new machine are the power set of states from the original machine. Start state is still Q0. The alphabet is still the same. The accept states are any state in the deterministic machine that contains any accept state from the original machine. So Q4 is an accept state. So the state Q1, 2, 4 is an accept state because among the states that it's made up of, it contains an accept state.
How do we handle having multiple accept states?
Well, so you have multiple accept states. Any of those accept states in any of the power set are going to be an accept state. That's the way we're going to handle it, and it'll work out in the end.
Supposing we are combining the states, so like Q2, Q3 will be one state.
Mm-hmm.
So Q2 is an accept state and Q3 is not an accept
Yeah.
state. So the final state becomes an accept state?
Yes. You already got what he said? So if in the original machine Q3 is an accept, I think I'm changing what you said, but it doesn't matter. If Q3 is accept and Q2 is not, and I'm looking at the power set states and I'm looking at the state Q2 to Q3, that is an accept state because one of the things that went into making it was an accept state. Right? And again, the way to think about it is in terms of these paths through the search space. We're just looking for a path that's going to land at one of the paths that could have led to an accept. Since it contains both, if we get there, then it's going to be an accept. Okay. So let's torch you a little bit more with some more nomenclature. Right? So how do we fill in the transition function? We have our original states. We have our original transition function. Now what we're going to do is create this new thing with a whole bunch of new states, which means we need to know that if I'm in Q3, 4, 5, and I'm looking at a B, where do I go? And I got to fill out the entire thing. So the way we're going to do it is to fill in the transition function in the deterministic transition function, a state that has the name 1, 2, 3, 4, 5, or 1, 2, 3, or 3, 4, 5, or whatever, right? And I'm looking at an A. Remember, the two parts of the transition table are the states and the alphabet. So what I'm going to do is I'm going to march through all the states, and I'm going to march through all the elements of the alphabet. It's going to be the union of the entries for all of the states that made that state up. What does that mean? So if I'm filling in the row for the new state Q345, I'm going to look at, for A, I'm going to look at what Q3 did for A, Q4 did for A, Q5 did for A, and I'm going to add all of those in, because I'm going to union them, into the transition for Q345. But am I going to put multiple entries in?
No, you're gonna get that set which has all those next states.
As in you're going to union
As in
and
3, 4,
combine it
5
or
leads
set.
to 1, 2, 4, 6. So
Right.
you're gonna accept that combination of 1.
Make sure everybody got that, right? So I'm not going to allow myself to put multiple entries in, because if I'm putting multiple entries in, what am I creating? It's a non-deterministic machine. This machine is going to be deterministic. So this loop, union over all ik, is finding the state in the new power set of states that is the right place to go for that element of the alphabet.
Will it be a single state at the end?
Yeah.
Will be singles.
And,
Well, let me, actually,
creating a new state.
hang on. Let me do an example, because I know this is going to, without going through the example, this is not going to make any sense. Right? So, for our example, Baaa, bang, right? The start state is still Q0, but it's not, so the curly bracket Q0 is not Q0 anymore, it's the Q0 in the new machine. Right, so the curly brackets, you see the curly brackets, you should be thinking, oh, state in the new machine. We still have A, B, and bang are our alphabet. The rest of the states are Q1, 2, 3, 4, Q1, Q2, Q1, Q3, Q1, Q4, Q2, Q3. You know how it goes, right? So it's the power set of all those things. We're going to use what's called the lazy method for doing this, and hopefully it'll make some sense, right? So the way we're going to do this is by simply marching through the table for the original machine, starting with Q0, using that union business that I just did. So what is the new curly bracket Q0 made up of? Q0, right? What does Q0 in the original machine do when it sees a B?
Q1.
Where is it going to go in the new machine?
Curly braces Q1.
Right? So the reason I'm going to call this a lazy method is because we're going to, instead of first generating a Mongo table, which is the power set, that power set business is just a fiction. What we're going to do is let's start with Q0 and see where things go. Right? So what just got created in the new machine is curly bracket Q1. The other ones are empty, right? Because there's no place to go from Q0 with an A or a bang. So we don't have to worry about them. But we just created a new state called curly Q1. So we'll put that there. Now, what does curly Q1 do when it sees a B?
Nothing.
Nothing, because Q1 doesn't do anything when it sees a B. What does it do when it sees an A?
Q2.
It goes to Q2. So we're going to create the state called curly Q2, and we need to enter the row for that. Now, curly Q2.
Q2, Q3.
Okay, let's make sure I step through this slowly. When curly Q2 sees an B, what happens? Nothing. When curly Q2 sees an A, what happens?
Q3.
So what am I going to create?
A new
New state in the transition.
Slowly. One person. Somebody who's following along. Anybody. One person.
Q2, Q3.
State
Q2, Q3, curly
Q2, Q3, right? So because if I'm in Q2 in the original machine and I'm looking at an A, I could either go to Q2 or I could go to Q3. But the name of the game here is we'll go to both. So we're going to create a state called Q2, Q3, and that's going to be where I go when I see an A and I'm in state curly Q2, Q3. If I'm in state curly Q2, I'm going to create and go to a state curly Q2, Q3. Now I have to add its entry. So in order to add its entry, if I see a B, nothing happens, right? If I see an A,
Only Q2, Q3.
right, just slowly, that loop on the previous slide says, this guy is made up of Q2, so I'm going to go up and look at this, and then I'm going to go up and look at this. So I've already created Q2, Q3, so that's okay. And it's also the case that if I'm in Q3 and I see a bang, I can go to Q4. Okay, and then if I'm in Q4, I'm done.
Let's say that Q3 had some entry for A, does Q6 or 5 or something.
Yeah.
How would that table change?
Well, at what point?
Just for that one line. Just the line
Or the
for
Q2, Q3.
Q2, Q3.
Yeah, so and if Q3 had an entry for A saying going to Q6,
Right.
right? So what would the state be?
Q2, Q3, Q6.
Q2, Q3, Q6. Right? So the way, and again, if you want to think about this in terms of weird temporal quantum mechanics, state that I'm ending up in is the state of all the places I could have ended up, right? So it's not just when I branch, I could go to Q2, I could go to Q3, then this one branches and this one branches. We're creating states that represent the simultaneous landing at all the places I could have ended up at. Good? So again, a couple of things to take away from just this one example, and I'm going to come back to it in a second, is we wound up in the worst case with the power set that we started out with 5. It could have been 2 to the 5, 32 states, but we ended up with how many states?
6.
5. Right, so we wound up the same number of states that we had to begin with. So even though the subset construction has some bad worst case behavior, the worst case behavior that's bad, and it does show up. I mean, most regular expressions that people do using Perl. How many people have ever done any industry level stuff with Perl, or interesting stuff with Perl, where you've got a regular expression that spans 4 or 5 lines? 2 lines, 1 big line. How many people have used Perl? I'm picking on you because you raised your hand. If you've used Perl for anything that's had any kind of practical basis, you get out and get a job in software, it's not going to look like BA star bang, right? It's some gnarly, long thing. And when you compile it and then determinize it, the potential is that the original machine that you had was nice and compact, and the new one is actually going to be close to the power set of the number of states of the original machine, which means that its footprint for the transition table can be rather large, right? So there's memory limitations here. But in most cases, the memory limitations are not the absolute worst case. There's more, but it's not horrible. In this case, we started out with 5, we wound up with 5, so clearly it's not horrible. Okay, everybody good? Does this mean yes? Yes. Okay. All right, so, sorry. Somebody stare at, oh, I'm sorry, go ahead.
So I was wondering, if we have a self loop in each of the state, is there any possibility that we might not reach any of the state in the transition table?
For a particular...
Yeah, for any particular sort of...
Yeah, so where that shows up, and somebody asked about it before, is the easiest way to think about where it shows up is with multiple start states, where there are paths through the machine that I don't get. I drove this because we had one start state, and it's a very simple machine. If you have multiple start states, then you have to do that trick of adding a start state on. The other place this has to be modified somewhat is by epsilon transitions, but we don't want to worry about that here.
Okay.
All right, so somebody who's artistic, stare at the new machine that I came up with and tell me how to draw it. And you can modify the upper one if you want. So this is Q0, and that's Q0. That's pretty much the same, right? And it goes to Q1, and that's Q1, so that's pretty much the same. Here I am doing it. Somebody else tell me what's going to happen.
2 and 3 are this in the same vertex or bubble or whatever.
Q2 has a bubble, so there's one, and then there's an extra one.
State Q2, Q3.
Yeah.
There's an extra one after there's another one after Q2 called Q2, Q3.
Right.
And so then that has the little circle around it, and then from there you can go to Q4.
Right. So all I did was I renamed Q3 to be Q2, Q3, and I put the self loop on it so that the A's are being consumed there. So this is just the machine we started out with last time, right? So the big all this hoo-ha is that the first machine I showed you last time was deterministic because it had the loop in the right place. I took the loop and put it in the wrong place for no apparent gain other than to confuse you and justify this entire lecture. And then you run the algorithm on it, and what you get is a machine that looks exactly like the one I started out with. That doesn't normally happen.
You probably were talking about this, but can you return to why we know this method is going to give us a state machine that accepts the same strings as the previous one?
I'm looking at the clock.
Yeah.
I'm going to say take this on faith.
Okay.
So, but if what you really want to do is have a proof that this accepts all the strings that the original one accepted and rejects all the ones that the original one rejected. And basically, it's not hard to give a proof for that. But this is a construction that I'm going to guarantee you will do the right thing. But I'm not going to ask you to prove that on a quiz. All right? Pretty good? So we basically have two basic methods that for dealing with non-determinism. Either you do a search, which is pretty much the way regular expressions are implemented in Emacs, or you do determinization, which is pretty much the way that everything is implemented in the rest of the Unix world. Now, there's also a subsequent step that's built into most of the modern regular expression packages that first we do determinization and then we do minimization, because even if you do this, you do wind up with a much bigger machine than you need, and it's plausible that states are being created in the construction that are not reachable. And therefore, the machine is bigger than it needs to be. So there's a determinization state and then a minimization algorithm that's run to compactify, that's a word, machine. Give it a smaller memory footprint. But again, we're not going to talk about that here. All right, good. I think I said all of that. So we're going to run very quickly through some other tricks that you can do with finite state machines. And I should say that if you really get into this kind of stuff, there's a finite state transducer package called the OpenFST package that originally came out of AT&T and migrated to Google and now is an open source package that does all this stuff. So even though I'm describing these algorithms, if you want to actually implement a system that does finite state stuff of the kind that we're using, nobody actually does this from scratch. You just go and get the open source package. It has all the tools that you need. It has minimization, determinization, and all the stuff we're going to talk about next built in. So you just specify in a meta language, this is what the machine looks like, and all sorts of magic happens underneath. So all of AT&T's speech recognition systems are built on top of this package, and a substantial amount of what Google does on their speech side is also built on this open source package, which we're not going to talk about here. But if you get fascinated by this, which nobody will, you can look there. Okay, so one of the places that non-determinism comes in is the motivation that often it's easier to write a set of regular expressions to solve subparts of the problem and then glom those solutions together in a way that may introduce non-determinism and not have to worry about solving the entire problem all at once, which is a good software engineering practice. The way this is usually implemented is by going back to the motivation for all this to begin with, that regular languages are languages that are basically sets of strings. We need some kind of way of specifying the set of strings that are in and the set of strings that are out. I'm using the word set over and over again because if you're allowed to use sets, you're allowed to use set theory. And so you should all remember all your set theory, right? So that's the way we're going to go about doing this. So this is the phone number example that I gave last time. Could it be parenthesis, area code, phone number, area code, dot, prefix, dot, number, dashes. You could add the country code on the front or not. You could put the country code in parentheses or not. There's lots of different ways of doing this. So I gave as a homework, scrape a bunch of web pages and find all the phone numbers and distinguish those from ISBN numbers and area codes and zip codes and country codes, and just give me the phone numbers, all and only. You'd have a hard time doing that by creating one giant regular expression. But anybody can write a regular expression for 3 numbers, dot, 2 numbers, dot, 3 numbers. Well, the dot's kind of tricky because you have to make sure the dot really means dot and not a meta character. Okay? All right. So the way we do this is by simply ORing them together. So you write one regular expression for each type. To represent all of them, it only has to be the case that one of them has to work, and that's the definition of OR. And so we're going to OR this machine with this machine, and the way that we OR machines is by writing a machine to do one thing, writing a machine to do the other thing, and then introducing a new fake start state and a new fake final state, and connect the fake start state to the start state of machine 1 by an epsilon link, and the start state, that new fake start state with the start state of the other machine, and the final states from each of the individual machines get tied to the fake final state, also by epsilon transitions. Clearly a highly non-deterministic machine, but if we want to make it deterministic, we just take this thing and just shove it through the determinization algorithm, and we get one giant deterministic machine. That's an OR.
Sorry.
Do you have to actually know how to do that? No, because the packages are written in such a way that you write the regular expression for type 1, the regular expression for type 2, you OR them together, magically it turns into a machine under the covers.
Sorry, it's non-deterministic just because of the forks there?
Just because, well, it could be the case that these guys were also non-deterministic. They probably don't need to be for this particular example, but they can be non-deterministic. But simply introducing this introduces non-determinism, right? So remember the way that this epsilon is going to work. If you put it at the beginning, in particular, doing an epsilon transition does not consume anything at the beginning of the tape. So basically it's saying, this timeline could work out, this timeline could work out. Let's try this one. If it works, fine. If it doesn't, we'll go back and try the other one. And again, obviously, the way the determination is going to work is the determinization algorithm is going to work is by creating all sorts of these meta states that represent all the possible states that you can get to. Good? Well, if OR works, then not must be a possibility too, right? So we're going to construct, if I give you a machine that accepts phone numbers, how do you come up with a machine that accepts strings that are not phone numbers?
Rejected by M1 is accepted by M1.
Any letters?
Well, so you're a software engineer, right? You're thinking about it the wrong way, right? So you've got a machine that is already in hand that does the right thing, and it's got an accept state in it. Now, if there's things outside the alphabet, so let's say that what I really mean is strings that contain all the alphabetic characters that could show up in phone numbers. We're not going to worry about A's and B's and that kind of stuff. You have a machine. If it's deterministic, the answer's on the slide. Anything that's an accept state becomes a reject state. Anything that's a reject state becomes an accept state. Does that work for non-determinism? No, because if you think about the logic of it, right, if I did that, the way non-deterministic recognition works is I only need one path to an accept state. In order to reject, I have to reject all possible paths. If I simply inverted everything, I'd be guaranteed to do the wrong thing. But, so the answer is no. But what I could do, sorry, I didn't give you the answer. So what's the right answer? The answer is no, you can't do it. But how would you make it work?
from the except states that we have in
Nope, it's too hard.
Determinize?
Determinize it, right? So you're just like, here's how you do it for a deterministic machine. You just flip all the states. I give you a non-deterministic machine. The flipping the states thing doesn't work. Well, turn it into a deterministic machine and then flip all the states, right? We can always turn everything into a deterministic machine, and then the simpler things work. What about intersection? Well, intersection is hard to visualize how you're going to do it using machines. Hang on. But we know from logic that A and B is the same thing as not A or B, or not B. I just told you how to do not. I just told you how to do or. So and is easy. Right? A and B is you negate A, you negate B, you or them together, and you negate that. Then you determinize, and then you minimize, and everything works out fine.
Could you also just do them, start with one, have an epsilon transition from an accepting state to the starting state of the next one? And then only accepts if it gets to the very end of all of it?
So
Can't parallelize that, though.
say what you just said again.
So you kind of put the machines in order.
Yep.
And then you just add an epsilon transition from the accept state of the former one to the latter one.
Right.
And then you accept if it makes it all the way to the end.
So what would that be?
Conjunction?
No.
2D8 dot B.
It's hard to draw it. So I think what you're saying is we've got, a machine that looks like this and a machine that looks like this, and we're going to tie them together like that. So it turns out that what that does is the way to implement concatenation. So let's say I want something that's going to match this and then match this at the end. So it's a phone number that's immediately followed by a zip code. Then I'm going to tie the machines together, and that's how I do the concatenation algorithm. But it's not doing an and, because at this point, we've consumed the tape. So we can't say, oh, you're one of these two, because we're already at the end of the tape. And what you'd have to do is some kind of way of rewinding the tape, and we're not going to try to do that kind of thing. I mean, you could, but it's too hard. All right, everybody totally befuddled? Yes, you're not supposed to nod to that. All right, so we're going to change gears a little bit and talk a little bit about, motivate a little bit about why this is relevant, why I'm even talking about it. And so we're going to give you a really baby lesson in morphology so the linguists in the class can just go back to sleep and close your eyes, because most of what I'm going to say they cover in the first 10 minutes of a morphology class. And a lot of what I'm going to say is wrong. So historically, FSAs and FSTs have been used, those are finite state transducers, so another tape, in the representation of lexicons, meaning big bunches of words. Okay. The original motivation for this stuff in the United States came from the need to represent large lexicons on machines that had very limited memory. And as I teach this class every year and look out over the crowd, I realize that this is starting to sound like historical computing. So has anybody used an IBM Selectric typewriter? Has anybody ever used a typewriter? Is anybody who's ever not seen a typewriter? So typewriters in the 1970s started to introduce spelling correction in various ways. And IBM and Xerox were the ones that did the most with it. One of the things they introduced was a very small buffer-like LCD display. So as you were typing, it was not immediately going onto the paper. It was going to this little buffer, and then as it emitted from the buffer, it went onto the paper. But if you got a spelling error, you could actually see it on the screen before you typed it, and you could have an opportunity to fix your spelling error, right? So you have a typewriter that knows how to do spelling correction. What do you need to have in order to do spelling correction?
Lexicon. The words.
Somebody say it. The words, right? In order for it to know that's spelled wrong, it needs to know what it means to be spelled right, which means it needs a big honking list of words. But we're talking about devices that had, I don't know, 500 bytes of memory, right? So that's an exaggeration. But nobody here remembers those days. You all have iPhones with gazillions of gigabytes of memory, so nobody worries about memory anymore. But it used to be an issue, right? If you want to put 100,000 words onto a typewriter, that's a problem, right? So you had to come up with fancy ways of representing lexicons. And that's where all this stuff comes from. It turns out that it's still very useful because you cannot represent all the words in Turkish because there's an infinite number of words in Turkish. And if I say there's an infinite number, then a list is not going to work, right? You could argue there's an infinite number of words in English too, and we're going to talk about that next time. All right, so got it? All right, so this is back to the baby morphology stuff. Morphology usually refers to breaking up words into their minimal meaning-bearing units. Normally, we can talk about those minimum units breaking down into two classes, stems and affixes. English affixes typically are limited to prefixes and suffixes. So you think about affixes as being the little bits and pieces that are glued onto the front and the back of the words. So dog, dogs. Anti-dog, anti-doggingly, anti-doggedly. You get the idea. Anti-disestablishmentarianism, right? Got it? All right. So the stems are the meaning-bearing units, like dog, and the affixes are these things that are glommed on in one way or another. Morphology, then, so there's stems and affixes. Then we typically break down morphological analysis into derivational morphology and inflectional morphology. Inflectional morphology is probably the stuff that you're familiar with if you've ever learned a second language or if you've ever introspected about your own language, so we'll talk about that first. Before we get there, we're going to talk about word classes. This is going to come back. I know I'm going through this fast. Nouns, verbs, adjectives, adverbs. How many are there? 7. Anybody remember the grammar school? Anybody remember the definition of your teacher telling you what a noun was?
Person, place, or thing.
Person, place, or thing. The thing part is dubious, or idea, which is really there trying to get away with smart aleck kids asking questions that they don't want to have asked. So word classes we're talking about turns out have a completely syntactic definition. You can't really define them semantically. But we're going to talk about things like adjectives, nouns, verbs, prepositions, because they're all going to bring along their own baggage for morphology. Okay? All right. So for inflectional morphology, what we're talking about is, for nouns, things like it starts out as a noun. After the inflectional morphology, it's still a noun. The meaning is different, but this is one of those linguistic terms, but the meaning is transparently related to the original meaning. So going back to my favorite example, you got dog, you got dogs. It's a noun, it's a noun. Dog is all talking about furry animal. Dogs is talking about more than one furry animal, but we're still talking about furry animals. Right? So in English, for nouns, the inflectional morphology is extremely limited compared to many other languages. Pretty much you got plurals and you got possessives. That's all you have to do with it, right? Dog, dogs. Dogs is a little bit of ambiguity because it could be one dog, two dogs, or the dog's collar came off. So I made a possessive out of dog by adding z on it to get dogs, the dog's collar. It's not two dogs. It's a possessive marker on the dogs. But for many other languages, you get markers that tell you the gender, that tell you how you're related to it, the number, all sorts of other morphological bits and pieces can get glommed on. Good? For verbs, it's even easier. You know, walk, walks, walking, walked. So it's basically the verb tense structure of the language. Is also part of the inflectional structure. Good? All right. So nouns are simple, verbs are slightly more complex. That's pretty much it for English. Lots of other languages are much more complex. And what this means is that in the early days of NLP, and we'll talk about the major algorithm that is a major hack called the Porter-Stemmer, there's techniques that work for English because English is so simple that allow us to do a lightweight morphology and not having to do very much. But it's not going to work for Hungarian, it's not going to work for Finnish, it's not going to work for Chinese, it's not going to work for lots of languages. So if we're going to do a serious job in a multi-language environment, this stuff's not going to work. But it works well enough for English. Okay, everybody happy so far? All right, so Except, of course, there's irregulars. And so irregulars, I say, English works like this, except it doesn't. So the plural of mouse is not mouses, and the plural of goose is not gooses. Past tense of catch is not catched. And the way these usually are dealt with is just by having an ad hoc list that says this language has this regularity, except doesn't work here. And over time, there's lots of examples in language change where these irregularities go away as the language evolves, especially if a term is a low-frequency term. So if a term is a low-frequency term and it's irregular, it's almost guaranteed that it's going to go away and become regularized. Because kids learning the language learn the rule, they never hear this obscure word, so why on earth would they ever come up with some kind of strange irregular for it? So the irregulars that live on are the irregulars like catch and caught, where it doesn't take very long when you're young to say catched a few times, I catched the ball, and then your mom screams at you. For second language learners, this is extremely difficult because it's very ad hoc. There's no set of rules to learn. There's just an arbitrary list of stuff that you have to learn. Good? All right. Same thing happens for verbs in terms of the inflection pattern. And here it's the case that there's a large number of high-frequency verbs that do have the normal pattern, walk, walks, walking, walked, walk. Other languages are much more complex from this, right? So even if you're taking high school Spanish, the first thing you run into is the verb inflection stuff. And it's like, oh my God, I don't want to take this class anymore. Can't we just speak English? Because it's too hard, right? So, but it's still finite. And again, in English, you have to learn these irregular patterns across verbs. Good? All right. So there are irregularities, there are rules. The rules are easy to capture in things like finite state machines. The irregularities are simply captured by adding extra arcs that do something weird. All right. All right. Now I'm going to run through this part really quickly because there's just no hope. But it's the part that should drive you crazy. So English derivational morphology is quasi-systematic. Again, this is a term that comes from linguistics, and when you hear a term like quasi-systematic, you really should, your skin should start crawling, right? So it means it's systematic, but it's not really. There's no way of writing down a finite set of rules. There's just an infinite number of irregular exceptions to the rules. It really looks like there should be a set of rules. But when you're learning this stuff, you're like, okay, I don't get it. Right? I'll give you an example in a second. There's irregular meaning change, which means it's very hard to predict that when a word goes under this morphological derivational process, what the meaning of the resulting word is going to be. And it's going to involve a change of word class. So when we went from dog to dogs, it was a noun, and it's still a noun. When we talk about derivational morphology, we can start as a noun, come out as a verb, start as a verb, come out as an adjective, start as an adjective, come out as an adverb, and have to be able to figure out what that meaning is going to be when it comes out. I'll make this all clear in a second as to why you should care. So if you have a word like computerize, that's a verb. And if I add ation on the end, computerization, that's a noun. Clearly, the meaning is they're related, and you can sort of see where the term derivational comes from. The meaning of computerization is derived from the meaning of computerize, and it's sort of clear what it means, but it's not totally clear. And as a speaker of the language, you have to know when you can say it, what the right circumstances are, and how you want to say it, right? Appoint, appointee. So if I make an appointment, the person who gets appointed as part of the appointment is the appointee. And I'm the appointer. That makes sense, right? Kill is a verb. The person who does a killing event is a person who's killed in a killing event. So now you see the quasi-systematicity, right? The person who's the appointed of an appointing event, it's perfectly okay to call him the appointee, right? Clinton's appointee for the Secretary of State is so-and-so. The victim of a killing, if you were writing a newspaper article and said the killee was 39 years old, right? But again, if you're a second language learner of English, how do you know that appointee is okay and killie is not okay? That's what I mean by quasi-systematicity. Clearly, there's a rule that says something about what sticking E on the end of a verb means. But where it applies and where it doesn't apply is fuzzy. All right, so nouns go to adjectives. Computation can turn into computational. Embrace can turn into embraceable. Computation, clue can turn into clueless. Right? There's lots of different ways of doing this, and it's not a one-step process, and this is why the finite state machines with loops come into it, because I can go from computer to computerized to computerization, and computer, in fact, comes from compute. So really, it's compute to computer, and if you look at an old dictionary, what's the definition of a computer? A dictionary from the 1950s. Somebody who computes is a computer, and that, up until roughly 1955, that's what the definition of computer was. So to compute is a verb. The person who computes is a computer. To computerize something is to mechanize the process of computing. And computerization is what you get if you need a noun. And this is all only looking at the suffixes. So if you have people out there that are against computerization, then they're anti-computerization. You can go on and on and on, right? So lots of examples of this. Now let's go back to clue for a second, then I'll give you some motivation for why you should care about this. So clue, perfectly good. What kind of word is it? Noun. So to not have a clue is to be clueless, right? How many people like clueful? Nobody? So I'm going to talk about what I mean by the question mark there. Clue, if I were to go and do a search of the web or to look at Twitter and searched for instances of clueful, would I find them?
Yes. Probably.
Yes. Right. Does that mean it's a word in English?
No.
Okay. You guys are prescriptivists as opposed to descriptivists. And the way to think about language, this is part of what you have to learn in this class. The metaphor for this is if you're taking a biology class, let's say on plant biology, you're not going to have a professor that says, at the start of our taxonomy, there are weeds and there are plants that we want, right? Because that's not the way biologists think about plants, right? Their dandelions are dandelions, right? The fact that people don't want them on the lawns does not mean they're not plants. The fact that you might not like clueful does not mean it's not a word. The only criteria we're going to have for whether or not it's a word is if people use it. Right, so if clueful's out there, then it's a word, and we have to deal with it. Right? So to have a clue is to be clueful. Right? How about to be the kind of person who can get a clue? So a person who can be taught is teachable. Right? A dog that can be trained is trainable. But clueable just doesn't seem to work right. Right? So if I went out to Twitter or I went out to the web and did a search for clueable, I know where the only hits would come from, and those are from the slide. Which would argue that it's a word, because it's out there, but by my own definition. Got it? All right, so that, I just want to introduce something else that we're going to come back to later in the class, the star versus the question mark. The question mark means that there's some issue that might lead you to believe that it's acceptable to some part of the population. And therefore, it may not be acceptable to everybody, but we're gonna say that it's acceptable, even though it's not clearly as good as clueless. And the star means not in the language. We want to reject this, right? So given this example, where is this going to have some kind of practical import? I know this is in the book, but and I sort of gave you the hint already with the IBM Selectric example. Those of you who write papers before you submit them, you do spell check them, right? And how does the spell checker on iSpell, ASpell, whatever your favorite spell checker on Unix work? And how does the spell check in Word work? Any guesses? Well, what would it have to have? A dictionary, which is, in this case, just a big list of words, right? So let me give you an example. In my thesis, all the way through to the published version of it, there was one place where I spelled grammar wrong, which is kind of embarrassing when it got pointed out. So it was Grammer. And it went, I wasn't spell checking it on Unix. So why did it go all the way through?
Because the grammar, the word might be added to the dictionary.
So you guys are great. So what they said, gram is a word. It's in the dictionary. So if gram is in the dictionary, what should be in the dictionary? One who grams. Right? So you double the consonant and add an ER. So if dig is in the dictionary, digger should be in the dictionary. The way the Unix spell checker worked at that point in time, it had about 30,000 entries. It had 30,000 entries of core words, and then a whole bunch of morphological rules. And the morphological rules were things like where you can stick anti on the front of, and ER in the back of, and doubling the consonant in appropriate places. So gram's a word, grammar is a word. Now, obviously, it's not stuck with that. You have to put, the way that it works now is you add exceptions. So gram is a word, grammar's a word, except when it's grammar. So you put X if Y except when Z is the way the Unix spell checker works. Now, the word spell checker has a slightly different flavor to it. And if you think about the way Microsoft writes, anybody here work for Microsoft? Software. Unix had a very tight philosophy that we didn't want to write a lot of bloated software. So the philosophy of, we'll start with a small list of words and then add on generativity to our spell checker. So if I see grammar, I'm not going to reject it because it's not in the dictionary. I'm going to see whether or not it could be in the dictionary because I know all these morphological rules that are encoded in finite state machines. Make sense? Words philosophy went the other direction. We don't need that. We'll just list all the words. And that didn't work out too well either, so they backed off of that. But there's still a tension where the Unix spell checker has a much smaller number of words, and the word spell checker has something on the order of 600,000-700,000 words. So they'll list every possible thing except where they can't. Good? All right. So let me show you some slides, and I'll come back to these next time. The way this is going to work for thinking about representing the lexicon is we're going to use finite state machines to do it. Accept strings are words that are in the language. Reject strings are words that are not in the language. So we're going to accept grammar, AR. We're going to reject grammar with an ER. We're going to accept dig, and we're also going to accept digger. We want to accept appointee, but we're going to reject killie, all just by using finite state machines. All right? So at a high level, regular words are easy because we're just going to accept them. Irregular words, we're going to accept them. Regular words with regular morphology are going to be accepted. So that's going to look like something like this. We'll start with a machine for nouns that simply says start state, regular noun gets us to Q1. Q1 is an accept state. Good. So if I say dog, dog's a regular noun, dog gets us into Q1, accept. Okay? If I say dogs, then dog gets me to Q1, the plural marker gets me to Q2, end of tape, dogs is okay too. Right? Oxen is an irregular plural noun, gets me straight from Q0 to Q2. Now this is an example where I was talking about last time of in building finite state machines, we talk about states and we talk about the alphabet they operate over. Here I'm asking you not to take the name regular noun too seriously, but how are we going to compile this down into an actual finite state machine? Well, I'm just going to take that regular noun arc and blow it up to the actual spelling of all the regular nouns in the language. So now the transitions are letters in the alphabet. If cat is a word in the language, then a transition for a C to some state and an A to an X state and T to an X state is a transition that leads to an accept state. And an S gets me to cats. That's good. Make sense to everybody? Now, if you look at that and think about the average American freshman in college, allegedly, knows about 250,000 words. Google claims that there are 13 trillion English words. It's really hard to believe. 13 million, sorry. Not 13 trillion. 13 trillion would be way too much. 13 million is way too much. So think about what this machine is going to look like when you list all the words in the dictionary it's going to be really big. It's going to be deterministic if we determinize it, and then we can minimize it. And it turned out this is the way that the problem was solved with the typewriter. And it's more or less the way that's solved in complicated systems that need representations of words where you have to have access to the morphology of the words. So you take the entire dictionary that you know about and you compile it down into a finite state machine where the transitions in the machine represent the characters. And then we add on additional rules to allow us to get things like computerizability without actually having to have computerizability in there. Good? Okay, I'm out of time, so we'll pick this up next time. Everybody got any questions about the class, the Moodle? Everybody working on the homework?